halos.
Thank you. Yeah, hello everyone, and welcome back after lunch. To make this fairly easy for you, the punchline of my talk is basically the same as the punchline of Martin's talk, that stellar halos are cool. There's tons of information in them, but we don't know yet how to get it out. And to get at all the information that's stored in the stellar halos, we need, one, probably better data-driven and machine learning techniques, but also two, we need more and better theoretical models to actually connect how galaxy formation histories connect to what's in the stellar halos and how they correlate with their galaxy. And so many of you know me as working on comparing large galaxy simulations to large surveys and working on star formation histories, and so kind of a different side. And that's one of the reasons that I wanted to talk about this today. But in my view, these are both connected. It's like you want to use the present day information that we get from any survey to learn about how the galaxies form, how individual galaxies form, maybe in some cases, but also how the population of galaxies formed and what the physics is that drives galaxy formation and evolution. And so to start from the large picture, we have a cosmic web. We have a halo environment forming in there. And this environment means that smaller halos are accreted into larger halos, which gives you this nice distribution of multiple connected galaxies and halos, satellites, and tidal debris in the halos. And then the galaxies inside are governed by a lot of additional physics with the gas, star formation, dust, supermassive black holes, secondary dynamical effects. And that can mean that the galaxy is still star forming or quenching. And so my question is, can we entangle all these different physical effects and learn from what we see of galaxies to actually get to the underlying processes? And here I've set it as different external and internal physical effects, but of course these are connected. And to give you two very close by examples of that, for example, this is a recent work on the star formation history for the Milky Way. And what they've done is looked at the star formation, or tried to infer the star formation history of the Milky Way disk. And they see these peaks in star formation. And what they show in this paper, or what they find intriguing, is that it looks like that might be at the same time or at similar moments as barycenter passages of the Sagittarius dwarf galaxy. And to give you another example, slightly farther away, is that with an amazing amount of information that we got in the last few years about M31 and its stellar halo, de Souza and Bell argued that M31 actually had a merger around 2 gigayears ago, which can be traced in a combination of effects related to actually the stellar populations in the halo, the giant stellar stream in the halo of M31, which is here, that its inner stellar halo is rotating, that there is what they see as the satellite that actually fell in is now a very compact metal-rich satellite, and again, a global burst of star formation in the disk of M31. And very recent kinematics from DESI seems to kind of support this rough idea. And in both of these cases, this is still obviously under discussion in the literature. But to me, they're interesting examples. But these are only 2 galaxies. So to actually get to general physics, we'd like to go further out. And that leads me to kind of the general point that stellar halos, satellites, and their tidal debris can provide a lot of information, sometimes separately, sometimes in addition to information that you get from the galaxy itself. And they can provide clues to a galaxy's past evolution and insights in lower mass galaxy formation of all the satellites that have fallen in. A lot of what we know from dwarf galaxy evolution is based on the Milky Way satellites. Actually, the extended streams and shells that are in the stellar halo are tracers of the dark matter potential and provide measurements on the dark matter halo properties. And there is a lot of work in looking at the moment in smaller and larger surveys to look for satellites, for example, in Saga and ELS, or for stellar streams. But as mentioned before, the low surface brightness regime is a discovery space for Euclid, Rubin, and Roman in the next couple of years. And to highlight that a bit more, I'll show in a bit more detail actually what Christian showed yesterday, that a few years ago, we took the current pandas data for the halo of M31, and we took a small region, and we inserted a stellar stream in there. And actually, in this case, we inserted 3 stellar streams in there that have a mass similar to the Palomar 5 stellar stream in the Milky Way, 5 times more massive version of that, and a 10 times more massive version of that. And this is the field that you get. You could maybe see one of the streams, I think.
I can see 2.
You can see 2? Okay, 1 or 2. It's slightly easier on the screen, on your computer screen, than here. That one. Ah, yes. Okay. Okay, so now we can use the same stellar populations to try to project what you would see with Roman, and then you see this. So this is just to illustrate that Roman, and in a less sense Euclid, is gonna resolve much, much more substructure. And in this case, these are not dwarf galaxy streams, these are globular cluster streams that are very thin, but you expect them to be numerous in halos like Andromeda. And so we could probably see these out to at least 3.5 megaparsec, which contains about 200 galaxies. And as Christian showed yesterday, we could even see gaps potentially in these streams out to 1 or 2 megaparsecs, which you can use as tracers of small dark matter subhalos. And as another example, these I showed these in my title slide a bit too. These are figures as a projection what you could see for Rubin. And on the left is actually an illustration of the process to make these synthetic observations from simulations. And the key thing that I want to show is that there is a lot of substructure, and even at that depth, the depth of Roman, including noise, the effect of the PSF, etc., you see only part of that. And so the deeper we go, the more we will see. And there is actually, there has been quite a bit of work to automatically classify these tidal features. to automatically look for interacting galaxies. That's one thing, but especially also to classify the tidal features that you see. But the main question is, how do we interpret that? And especially if we're going to see, like, these are examples of very nice examples of individual things that you could see. This kind of thing is way more messy. And what you can already see in the literature is people call it different things, whether it's a plume or a tail or a stream or a whatever. It's sometimes really hard to tell. There's no good definition. And the question is how we're going to interpret that on a very large scale. So if we look at the theory space, there's a lot of different ways in which you can look at stellar halos or work on stellar halos, where we can look at large cosmological galaxy formation models that have many, many galaxies, but they have fairly low resolution. They do have the cosmological context. You can go to slightly smaller zoom-in simulations that look closely in one galaxy or in a few for a few galaxies. These have much higher resolution, and so they can follow the formation of these faint features much, much better. And actually, there's also, with lower resolution, also comes an issue with whether your dynamics is actually traced correctly at some point. So higher resolution is important. And all the way at the other end, there is dynamical modeling in isolation, which is often happening in static, spherical, or in triaxial in a relatively simple way, galaxy halos, but where you can model every individual star and model the dynamics of every individual star. So very high resolution. And that's often used for the modeling of stellar streams. And that there is a space here in between where you'd like to optimize the flexibility of your models and the size of your data set, but still try to get a reasonable resolution, but also a reasonable sample size. And so what Martin showed just before lunch is that one way to do this is to go to dark matter only simulations within top empirical galaxy formation models. And that allows you to increase size, keep a reasonable resolution, have some flexibility in your galaxy formation model, but it's also still can be challenging to get to large sample sizes, and you're limited by the dark matter resolution in that case. And another avenue that fits in between here is semi-analytic models, and that's what I wanted to talk about for most of the rest of this talk. So I've been working on building a semi-analytic model that predicts the evolution of tidal debris in a galaxy halo. And for that, I use as input a semi-analytic galaxy formation model, as well as orbits that are taken from a distribution from cosmological and body simulations. And these are actually pretty well sampled. So I take this one, but many papers find this similar distributions. So that's pretty robust. And so over cosmological time, I have a main halo that's growing, that has satellites falling in. And then for those satellites, I follow the evolution of the debris, what their morphology is, and in the end, whether they would be observable or not. So estimate how fast the dark matter halo strips, how long it takes for the stars to strip, how they form into a stream or a shell, how that stream or shell evolves, and then what the final surface brightness is. This project has gotten stalled a little bit during organizing this program, but I hope to get back to it. So many of the figures are still preliminary because I keep updating and adding more and more elements to the model. But so to show you an example how this works out, so on average, this shows the average number of tidal features per LMC over time, and these different categories can evolve into each other. So you can have a surviving satellite that at some point is going to form a stream. And actually streams at some point can form shell-like features inside of them. And eventually a stream or a shell becomes phase mixed into a relatively smooth stellar halo. And so on average, at the end, there's a few shells in this mass range, and this is LMC-sized galaxies. There are a number of features phase mixed into a smooth halo. There's about 5 to 12 surviving satellites in this case. Is that right? Or is that streams? Yeah. No. Actually can see the colors on this. No, there's a few satellites and there's about 10-ish stellar streams, which doesn't mean, the question then is, would these be observable? How bright are they? How massive are they? And so what I did is make predictions of surface brightness and take a look at the limits for Euclid, Rubin, and Roman, and see if the tidal features that will be there in many LMCs, even LMCs in this case, whether they will be observable. And so this is again Euclid, Rubin, and Roman. For Euclid, I took the visual band, the R band for Rubin, and the H band for Roman, which is actually the best. Turned out to be the best in this case. And so at the limits of the surveys, you can see how many, even LMC-sized galaxies, so relatively low mass, how many would have visible tidal features that are visible based on their surface brightness in the surveys that are planned. And roughly, that turns out to be about 50% have at least one feature. For higher mass galaxies, you expect this to be way more. Similarly, so the nice thing about semi-analytic models, there are many assumptions in here that have to be taken into account, but the nice thing is that you can start playing with the galaxy formation physics and with everything you do basically in the model. And so similar to what Martin showed, so here's actually that figure again, where if you change, in this case, the low mass slope of the stellar mass to halo mass relation, the diversity or the spread in the stellar halo masses changes. So I can do a similar thing in this case, and if I make this stellar mass to halo mass relation steeper, then you almost won't see any tidal features. And so to me, that's the interesting part of the model eventually, is I can play with the physics, see what it does, and look what are the constraints that you will get from this large sample on the physics. In the last minute, I wanted to highlight some work by a student, Tjitske Starkenburg, who's a grad student at Texas Christian University, who will be at Carnegie next year. And she's been looking at how streams evolve, if existing streams evolve, if there is a major merger. And this is one of the elements that's almost never taken into account in the modeling of streams. And it's one of the things that I can now fold in to this cosmological model. And what you can see is the streams do crazy stuff. At least some of them. They move out, they change morphology. It can be very weird. And so we're trying to figure out what happens exactly. They move around in energy and angular momentum space, and they actually change in energy depending on the major merger that they experience. So my takeaways are stellar halos have a lot of information. Many galaxies will have observable satellites and tidal features, but we need larger, more flexible theoretical data sets to be able to even help interpret this. The other thing is we need better applied data-driven techniques to bridge from the observed substructure to galaxy physics and galaxy formation histories. And I have some toy projects that I'd love to chat more. And lastly, if you're interested in organizing a program like this, please feel free to bug me about it. Thank you.
Okay, thanks. Yeah, let's start up front. Here, you can use this
one. Josh Peak here, as always. So you talked about counting the number of features you might see and how that's really important for understanding what's going on. Then you said we have these really wacky streams that we get from major mergers. I think you know where I'm going with this. You know, what people like to do with things that they can see is make lists of them and then start cataloging them and saying, this one looks like a shoe, and now I'm going to write a paper about shoes. So my question is, like, what does quantitative morphology look like when we have streams at scale?
Yeah, so that's a question that I don't have an answer to yet. And I think that we need to go and figure out. So the reason that I list the number of features you could see is just to highlight that there will be things you can see, and actually quite a few. That it's more than, oh, you see maybe one stream. But it will be much more messy than that. So one thing is we need to figure out better statistics to think about this for larger samples, which can be based on the amount of light you see at certain surface brightnesses, or other ways to quantify the substructure without having to look for real individual tidal features. Because another is for the Milky Way, and maybe M31 eventually, we will have some 3D information for the Milky Way, we have that. But further out, that's not going to happen. So disentangling streams or features is very, very hard. So we need to find some other statistic or maybe we don't want statistics. But we need another way to start learning about it and to start comparing it and get a big sample.
Yeah. So I think it's as good a time as any just to give Tjitske a huge round of applause for all the months of work.
Can you extend that to all the organizers?
But especially Tjitske, because without her, this whole thing would have never gotten started. And so I want to thank you for that. And I'll also ask a question, which is related to diversity. Also related to Martin's work, to ask about orphans and when you call a satellite disrupted, because at least in the empirical models I've worked with, including Ben's, there's always a question about when do you call a satellite actually disrupted and when you don't, and how does that factor into the degeneracies that you're seeing in the diversity of stellar halos and the information that you'd be able to get from observations?
Yes. So So in the model, in my semi-analytic model, I'm calling something disrupted when the tidal radius is within the stellar half-mass radius, basically. But what you see is you then see an evolution of a surface brightness of a stellar stream. And what you can think of that is like initially there's still kind of a satellite core, but there's two tidal arms evolving, and that will slowly grow over time into a full stellar stream. But again, I think there's no one answer to the question, when is something starting to disrupt? But also there's no answer to when is something fully disrupted, because the same issue arises to when is something phase mixed. When do you call something? It's like anything that's too faint to see is essentially phase mixed in the model. It's within the background stellar halo, which is not perfectly smooth. But yeah, so I do make an assumption about it. It may not be the best one. Yeah, I don't think there's an exact answer.
Yeah, thank you for the talk. I find fascinating that you can just, constrain the slope of the dark matter stellar mass or halo mass stellar mass relation just by counting stellar streams or close surface brightness features. I'm also a bit surprised that it's so neat. So it's just, I guess the scatter might play a role, quite important role there, and probably wash out some of these huge trends. So I was wondering how you take into account. And there might be also other parameters, right? So it's not that simple. It can be.
No, of course it's not that simple. So in this case, I'm actually not changing the slope, but I'm changing a star formation efficiency parameter for dwarf galaxy formation, which ends up changing the slope. But of course, that's just one parameter I change, and there are many other parameters that will influence what the statistics is that you see. So no, it's not that simple, and it's not a direct relation. It's just a very clear example that the physics that you assume does change the outcome. And so there is some information on the physics, but what and how exactly is not as clean.
So can I comment on that related to the comment I made on Martin's talk? And I'm just trying to wrap my head around this a little bit because, so beautiful talk. And it's clear that there's information in these stellar halos. And I'm thinking about this a lot myself as well. But following on the comment I made earlier, I thought that most of the stellar halo in Milky Way objects is from 1 to 3 objects. And that's probably not more in LMC mass systems because of the steepness of the stellar mass halo mass relation. So is there really a lot of information there that isn't in the bright end of the conditional stellar mass function for those hosts? Like clearly there's some, but it's not probing fainter, I don't think.
No, not necessarily.
At least not in external galaxies.
Yeah. No, I'd agree with that.
Okay.
Yeah.
It's still very interesting.
Yeah. It's just additional. You do get additional information. It's not necessarily better than looking at the smallest galaxies that we see around us. What I will say is that yes, most of the stellar halo is built up out of a few objects. But those few objects are more massive mergers, which happen more quickly, and the smaller objects, especially if they are more in the outskirts, will survive for longer. So there's actually quite a chance that if you see stellar streams, that those are from fairly low mass objects. So in that sense, yes, I think there is definitely more information. Yeah.
Okay, maybe one very quick question while Joe gets set up. Go ahead.
Yeah, just a 1 second follow-up question. So based on Risa's question, I'm wondering, Tjitske, if there's any information about metallicity, could you then go to select out the lower mass components or the things that came from the super low mass end?
So yes. Again, metallist. So there's a few distinctions. So for resolved stars, metallicity would be very helpful. The further away you are, the harder this would get, but there are some color selections you could do, even just from photometry. The other problem is that most objects in any stellar halo are all metal poor, or all fairly metal poor. So the distinctions become really, really hard. And which is actually why finding substructure in the Milky Way halo is also still very hard, because the metallicities are not always very different. Yeah, so it is a useful addition, but it's not, it doesn't, not in all cases. Yeah.
Let's thank Tjitske again.